Now here's an example of sequence of functions that can converge almost everywhere, but not in measure. So we consider the measure space now will be the whole real line, not just the interval like we did before. And the functions you're going to consider are functions that look like this. So here's the set of real numbers, and the function for each n, the function is something that looks like this. So the function has this shape, and well, we call it the traveling wave because it's just this little square here. And of course, as n increases, this will just show up here, then here, then here. So it's traveling, it's moving in that direction. And now we see whatever little omega we fix here in this measure space, well, eventually this traveling wave will go past that point. And once it goes past that point, after that, this function will be 0. So that means fn of omega, it will be fn of omega will be equal to 1 just once, and then 0 after that, before and after that. And of course, this means fn of omega converges to 0. So it converges to 0 for every omega. So for every omega also implies for almost every omega. However, if here we take epsilon equal 1/2, let's call this epsilon equal 1/2, and we see when is this function different from 0 by more than 1/2, we get this whole set here. So the set of omega such that fn of omega minus 0 is larger than 1/2, this set equals the set n plus 1. And if we compute the measure of the set, it equals 1. And as we know, of course, 1 does not converge to 0. So fn does not converge to 0 in measure. Now here's an example in the other direction. We have functions, a sequence of functions. So it's a function, you need two indices to construct the function, but then after that you can order them like this and keep going. So this is a sequence of functions, and they look like this. The first function is just constant on this whole interval from 0 to 1, constant equal to 1. And after that, there will come two functions. They will both have this stick here of length 1/2. The first one will have the left half of the interval, and the second one will have the right half of the interval. Okay, so now we have already 3 functions in our sequence, and now I'll add another 4 functions to our sequence. It will be sticks here that have length 1/4 instead of 1/2. And now we start with the first quarter of the interval, then I move on to the second quarter, then the third quarter, then the last quarter. And then, well, after that you can see we're going to have intervals of length 1/8, and I will have the first eighth of the interval, then I'll have the second eighth of the interval, then the third, fourth, etc., until I have the eighth of the interval. And then we keep doing this. So each time we have to include more and more functions in the sequence, but this defines a sequence. And since we need really 2 indices to construct the sequence, the first index is n, because this is 2 to the minus n, the length of this interval. And Now we have some k that tells you which piece of these 2 to the minus n intervals will take the value 1, so that the others take the value 0. So I have this n and k to describe these functions. And here would take k equals 0, and here would take k equal 1, and here would take k equals 0, k equal 1, k equal 2, k equals 3. So this 3 here is this 3 that we see here in the numerator, whereas the 0 here is just this 0 starting point here of the interval. So you see that k goes from 0 until 2 to the n minus 1. So there are in total 2 to the n such bits. And once we are done with all these k's, then what we do is we increase n. We increase n. And who is n? Well, here n equals 0. And this has to do with the length of this interval being 1 over 2 to the power 0, which is just 1. And here we have n equal 1, which has to do with the length of this interval being equal to 1 over 2 to the power 1. And down here we have n equal 2, which is related to the length of these intervals being 1 over 2 to the power 2. So this describes a sequence. It's not very convenient that it has two indices to describe it. But now once we have the sequence indexed by both n and k, we can now re-index it so that we have just one j. Let's choose j to index this sequence. So this will be j equal 1, j equal 2, j equals 3. So just order them sequentially like this. J equal 4, j equals 7, and then it keeps going. And the point of this is to say this sequence fj, they converge to 0 in measure. And why is that? Well, because fj minus 0 the set when this is larger than epsilon, this set, if we look at the measure of this set, it will be 1 over 2 to the n. And well, how are n and j related? Well, they're related in this somewhat complicated way, but what matters is n tends to infinity when j tends to infinity. Because here we have j equal 1, 2, 3, 4, 5, 6, 7, and then when j equal 8, already we have n equals 3, and so on. In fact, each time j is equal to 2 to some number m, that's when n will change. That's when n will change from m minus 1 to m. So it's increasing slowly, but it's increasing and it's going to infinity. So the only point here is to say this 2 to the n, this n, this 2 to the n here, the n depends on j. And when j tends to infinity, this will tend to 0. So this is to check that it does converge to 0 in measure. However, it does not converge to 0 almost everywhere. In fact, it converges to 0 nowhere. This function does not converge to 0. In fact, it only converges to 0 at one point. That's the point 0 here. Because the function is always 0 at 0. But if we fix any other point, and we fix, suppose we fix any other point, let's say we fix a point here, so we have this dancing wave, we refer to it as dancing wave. So we see here that, well, when we fix the point here, then the function, first it is 1, then it is 1 again, and now once the wave has passed past this point, it's 0. And then you might think, oh, okay, now it's 0, it's going to stay 0 forever. But that's not true. Here comes the wave again. You're 0, but you're 1 again. And now after the wave is passed, we're 0 again, 0 again. And if we go one more level, it will be 0, 0, 0, but then it will be 1 again, then 0, 0, 0, 0. So it will be 1 again and again and again, even if it's getting less and less frequent. But so this fj of omega will be equal to 1 infinitely many times. And if we go back here, this is in contrast with the traveling wave, where the function was 0, was different from 0 only once. Here it is equal 1 infinitely many times. So it means for every omega which is not 0, so this is the only point here where this does not work, we have fj of omega does not converge to 0 as j converges to infinity. And since it does not converge to 0, and of course it does not converge to any other number because it's 0 most of the time.